Hello everyone. Today we present our project, Automated Security Patch Backporting for the TensorFlow Library. We are Team Saga Decodagos. So, what is backporting? As this diagram illustrates, backporting is the process of taking a fix from a newer software version and applying it to an older, stable version. Security backporting, specifically, is crucial because it patches critical vulnerabilities in these older versions that are still in wide use, keeping them secure. Our main objectives for this project were: first, to implement a tool that automates the security patch backporting process. Second, to develop a method using a large language model to accurately backport these security patches. And third, to create a new security backport dataset for machine learning libraries, which can be used as a benchmark to evaluate backporting tools. Our methodology started with creating a comprehensive security backport dataset for TensorFlow. We began by web scraping security databases like Vullert, NVD, and SNCC to gather an initial set of security patches. Next, we used a script to automatically find the corresponding backports for these patches in older TensorFlow versions. When the script found a potential backport, we would manually confirm if it was correct. If it was, we added it to our dataset. If the script couldn't find a backport, or if the one it found was incorrect, we would then manually inspect the commit history to find the correct one. Once confirmed, it was also added to our final dataset. Our tool is named IntelliPort. It takes a mainline patch and the target version as inputs. The process involves three main steps. First, it identifies the exact location in the older code where the backport should be applied. Next, it generates the backport patch itself. Finally, it applies this generated patch to the correct location. It's important to note that our approach performs this backporting at the function level. Here, you can see the high-level architecture of IntelliPort. We start with the pre-patched mainline function and the code difference from the security patch. We then use clone detection on the target version to find the corresponding function that needs to be fixed. These three components, the mainline function, the patch diff, and the target function, are combined with natural language instructions to create a detailed prompt for an LLM. The LLM processes this prompt and generates a new diff, which is then applied to the target function to create the final backported patch. To accurately identify the backport location, we first take the mainline patch and extract the functions that were changed. These functions are then vectorized. Next, we parse the target version source code, extract all of its functions, and vectorize them as well. By comparing the vectors of the changed mainline functions with all the functions in the target version, we can rank them by similarity. The highest ranked function is identified as the correct target for the backport. Our final dataset consists of 267 backports, which we classified into 5 distinct types. As you can see, Type 1 and Type 2 are the most common. Type 5, which involves logical and structural changes, is the most complex and challenging to automate. The scatterplot shows that even simple backports can take a significant amount of time to be applied manually, which underscores the importance of automated tools. Analyzing the backporting time frame revealed that the process can be very slow. While the shortest time was 0 days, the longest was 99 days, with an average of 22 days to apply a patch. This long delay leaves systems vulnerable. Here are the evaluation results for our tool, IntelliPort. The table shows its performance across different metrics, including code blue and exact match, for all 5 types of backports we identified. We also compared our results with a state-of-the-art rule-based tool called Fixmorph. While Fixmorph performs perfectly on the simplest Type 1 patches, our IntelliPort shows stronger results for the highly complex Type 5 patches. This is because the LLM gives IntelliPort superior generalization power compared to rigid rule-based systems. Our tool does have some limitations. It currently generates patches function-wise, cannot handle newly imported headers or libraries, and its performance is tied to the underlying LLM. Finally, it is currently focused only on C++ files. In conclusion, our work makes three key contributions. We are the first to specifically address patch backporting for ML libraries. We have created the first benchmark dataset for this domain. And we have developed IntelliPort, an ML-based backporting tool whose underlying technique can be generalized for other backporting tasks. Now, let's see a quick demo of IntelliPort in action.
So this is the demo about IntelliPort extension. So we are in the VS Code now. So the extension is being installed here. So in the VS Code, we can clearly say we are in the tag 2.19. So it is the latest version. So what we can do is we can go to the command palette, then go to the backport to command. So now we have to enter the commit hash. For now, I will choose this commit hash for now. So let's go to the extension again. So we can go to the commit backport to command, then we can paste it here. After entering the commit hash, the versions tags are shown here. So we can choose any particular version. For now, I will choose 2.15 tag. Now the process is automatically done. So in the right bottom side, we can clearly see the progress. Let's go wait for that. So very first we have check out the tag, then call in the backport API. So API call get successfully. So we have the response now. So let's wait for it. So now the file is touched here. So in this message, it is clearly say that. So let's go to the changes file. So here, so in this file, we can clearly see the changes here. So in the left side, we can see the pre-patch versions of 2.15. So in the right side, we can see the post-patch version. So